Hi, we're going to continue with higher level acid and base theory, and we're going to talk about buffer solutions and problems with buffers. So a buffer solution is defined as a solution that has or experiences very little change in its pH when small amounts of acid, of strong acid or strong base, are added into the solution. Now, the reality is that if you have pure water or a non-buffer solution, if you add a small amount of strong acid or strong base, the pH is going to change dramatically. So if you add 1 milliliter of concentrated hydrochloric acid into a liter of water, the pH drops very significantly from 7 to about 2, depending on the concentration, or even 1. Similarly, if you were to add a concentrated solution of sodium hydroxide, the pH would go from 7 to somewhere in the vicinity of 12, 13, or even 14, depending on the concentration of this hydrochloric acid, of this sodium hydroxide that was added. But if you do that to the same amount, to the same volume of a buffer solution, and let's say that the buffer had been at 7, the pH change will be probably in the hundreds of a pH unit, as opposed to several different pH units. So buffer solutions are very important for keeping stable pHs, and it's actually one of the things that we as human beings use in our blood. We have a buffer system in order to keep the pH of the blood at a very close to constant 7.35, which is what we need. We need our blood to be ever so slightly basic for us to have our chemical reactions take place properly. For most cases, buffers are the solution of a weak acid and its conjugate base, so a salt of its conjugate base. You can also have a weak base and the salt of its conjugate acid. Alright, so you need to have both partners in the conjugate pair present for a buffer solution to exist. And Le Chatelier's principle is going to rule which direction the concentration of acid and conjugate base are going to move in order to keep the pH in a very small range and very close to constant. So I want to give you just very quickly examples on the next page that I've done. This is not present in the handout that I gave to my students, but I really want you to see this. These are some solutions that would be buffers versus solutions that are not buffers. Here we have a solution that contains acetic acid or ethanoic acid and sodium ethanoate. Because we have weak acid and its conjugate base, that is going to be a proper buffer. But if we have a solution of a strong acid and a strong base, a strong acid and a strong base, that is not going to be a buffer solution. I'm also going to add another not buffer solution that is not there. If you put a strong acid and its salt of its conjugate base, that's still not going to act as a buffer. So you have to have a weak acid and the salt of its conjugate base, like we have in the first case of the buffer solution column. Now you could also have it for bases. All right, you could have ammonia and ammonium chloride, and that is a conjugate pair of weak acid and its conjugate, weak base and its conjugate acid. So therefore that is also going to act as a buffer. All right. Now there's two here that may look more surprising. If I have ethanoic acid and sodium hydroxide, but the ethanoic acid is in excess and the sodium hydroxide is the limiting reagent, it means that it's going to run out. That is going to produce a buffer. Why? Because as the sodium hydroxide reacts with the ethanoic acid, it's going to form sodium ethanoate. Now, in the resulting solution, because the ethanoic acid is in excess, there will be sodium ethanoate and acetic acid or ethanoic acid left behind with no sodium hydroxide, because it will all be consumed. Similarly, in the reaction below, ammonia and hydrochloric acid, if the hydrochloric acid is the limiting reagent, will form a buffer solution. Because you will have ammonium chloride being formed. All right. In the side of not buffer solutions, it is important to notice that you can have, just because you have a weak acid and the salt of a weak, the conjugate base of a weak acid, does not mean that that's going to be a buffer. They have to be paired. They have to be a conjugate pair. All right. And be careful, because sometimes they look very similar. Here we have ethanoic acid with sodium propanoate. All right, so do not fall into the little IB tricks in the multiple choice kind of questions. Or here, phosphoric acid and disodium or sodium sodium hydrogen phosphate. All right, because this is not the conjugate pair. You would have to have one sodium and two hydrogens for that to be the right conjugate pair. Even if you have ethanoic acid and sodium hydroxide, if they're in equimolar amount, all right, meaning equal number of moles of each, that's going to produce only sodium ethanoate, and there's going to be no leftover acid. That does not act like a buffer. So you need to have a weak acid and its conjugate base, or a weak base and its conjugate acid. All right, wonderful. So let's go ahead and continue. If we are making an acidic buffer that is composed of a weak acid and the salt of its conjugate base, when we dissolve them, you are going to actually make the solution. The solution is going to be ever so slightly acidic. All right. So you're going to make buffers that have a pH below 7. All right. Now, the equilibrium that you're going to establish is a typical equilibrium. Acid goes to H plus the conjugate base. But in this particular case, you have a concentration not of 0 for the conjugate base, but you have an initial amount that you put into the solution. So you have initial concentrations of the conjugate acid, of the acid, and of the conjugate base. All right. Now the counter ion for the salt is never going to be included. Normally it's going to be sodium or potassium. It's going to be something that is a spectator ion, and we are not going to include them in there. So I just used letters in this case to give you a more general example. I will give you an actual example with numbers in just a moment. All right. Now those are your initial concentrations. The concentration of the acid, which is N, the concentration of the conjugate base, which is P, and as this reacts, it doesn't really matter which way you're putting it, but hopefully it will be minus x plus x plus x, and you get values that the concentration at equilibrium for the acid is going to be N minus x, the concentration for H plus is going to be x, and the concentration for the conjugate base is going to be P plus x. In most cases, because we are working with weak acids, the value of Ka is going to be very small, and therefore the value of N minus x and P plus x are going to be approximated to N and P respectively. All right, so that simplifies what we're going to be writing, and we can write our equation. All right, remember our statement, we always write our value or our expression for Ka, which is the concentration of H plus ion times the concentration of the conjugate base divided by the concentration of the acid. That statement would become then x times P divided by N, which are x is the unknown, P is the initial concentration of the conjugate base, and N is the initial concentration of the conjugate acid. We are really interested in the value of x, because if we have x, that's the concentration of the H plus ion, and we can use it to find out the pH. Right? Now, because most buffers do use a value of Ka that is very small, and we can use the approximation, we can simplify all of this, all right, into what is called the Henderson-Hasselbalch equation. Now the Henderson-Hasselbalch equation is not, unfortunately, on your data booklets. It is the most important equation for acid and bases, and yet you look at your equation there and it's not present. So I would recommend, if one of the few equations that you need to memorize or that you should memorize is this one, because it will help you work with buffers very quickly. The pH of a buffer is going to be equal to the pKa of the acid, all right, plus the logarithm of the concentration, the initial concentration of the conjugate base over the concentration of the acid, all right? And why is this all like this? This sounds a little bit crazy, all right? But it actually, in class, I will demonstrate for you guys. I don't want to spend a lot of time on that right now. But how do we know that? All right? It has to do with those values that we have here, the expression that we have up here for the expression of what is Ka. All right? So let's look at an actual example. All right? So if we make a buffer solution in which we have 100 milliliters of a 1 molar solution of ethanoic acid and 100 milliliters of a 1 molar sodium ethanoate solution, all right, we can find out what the pH of the resulting buffer is going to be. All right, first of all, we need to find out what are the concentrations going to be after we finish mixing. Because we had 100 milliliters of one solution, 100 milliliters of the other solution, it's obvious that what's going to happen is that the concentrations are going to be halved, because the total volume is going to go from 100 milliliters, or 0.1 decimeters cubed, to 0.2 decimeters cubed. All right, so you can see here the very first thing that we need to do is make sure that we calculate the concentration of the acid and the conjugate base after mixing the solutions. Since total volume is 200 milliliters, all right, molarity 2 is going to be equal to the initial molarity times the initial volume divided by the final volume, all right, which we have over here. In both cases, the concentration is going to be 0.5 molar, and this is in this case because I chose easy numbers, so we don't have to worry about too many of the other things. Once we have the concentrations after the reaction has been mixed, and sometimes you're going to have the volume and you're going to just put solid salt into it, so you don't have to worry too much about changing the concentration of the acid, but you would need to calculate the concentration of the conjugate base. Once we have those concentrations, we can do our equilibrium analysis. In this particular case, the concentration of the acid is 0.5 molar, the concentration of the conjugate base is 0.5 molar, so we're going to write them in their respective places. The concentration of H plus is 0. We're going to say minus x plus x plus x, and 0.5 minus x is approximately 0.5, and oh, here's a typo. We should write plus x, and that is going to be, and 0.5 plus x is approximately going to be 0.5 as well, because we're using very small value of Ka. Remember, the value of Ka for ethanoic acid is 1.7 10 to the negative fifths. We calculated that in one of the previous videos. All right, so we write our equilibrium expression as usual. We always write the equilibrium expression, and if we wanted to do the analysis fully like this, we can get that the pH is going to end up being 4.77. Now, we can also do this much quicker if we just put our values into the Henderson-Hasselbalch equation. All right, if we put this into the Henderson-Hasselbalch equation, we get that pH is equal to pKa over the logarithm of the concentration of the conjugate base over the concentration of the acid, because the concentration of, in this particular case, of the conjugate acid and conjugate base are the same. Those will be the natural will be the logarithm of 1, which is 0, and you end up that pH equals pKa. All right. Now there's a small difference in the values here, is because I used slightly approximated value for the Ka on the top equation. All right. But if you were using the exact value, you would get exactly 4.76. So notice something interesting. When the concentration of the conjugate base and the concentration of the conjugate acid are equal to one another, the pH equals the pKa of the acid. And that's kind of a really important bit of information. All right. So whatever ratio we make of conjugate base to acid is going to affect the pH of the buffer. So if we change that ratio, we can change the pH of the buffer. If we add strong acid to this acidic solution, all right, what is going to happen is that we are going to consume some of the conjugate base, because acid reacts with base. All right, and what happens when we consume some of the conjugate base? We are going to make some more of the acid. All right, so let's look at how this problem would work, because now we're going to be adding H plus, and there's going to be H plus also in the initial equation. So let's say, for the sake of doing this problem, that we are adding 1 milliliter or 1 centimeter cube of 1 molar hydrochloric acid to the previous buffer that we had done. All right, and so we want to know what is the pH that we're going to result, how much it's going to change by. All right, so, well, we know that the initial concentrations were 0.5 molar, and the volume that we had is actually 0.001 decimeters cubed. And so the concentration change is going to be very, very small, but nonetheless, we're going to calculate the new concentrations for everything, including the acid that we added, because the acid that we added, more importantly, is changing concentration significantly, because its volume is going from 1 milliliter to 201 milliliters in total, which is the total volume. All right, so let's look at those calculations very quickly. And again, you guys have those in your data booklets or in the handout that I gave from class, so you can follow along. We are calculating the new concentrations of the acid and the conjugate base. Okay, and so I call them concentration 2, because it's not the same as the initial concentration. And we're also calculating the new concentration, and this should actually, apologies, say concentration H2 as well. That would be the new concentration of the acid. And now we're going to do our typical equilibrium analysis. We're going to have the same equation that we used before. Acid goes to H plus and conjugate base. All right? But notice, in this case, we have every one of those units is actually going to have a concentration. Because we had the weak acid and the conjugate salt, all right, the salt of the conjugate base, but now we added a little bit of H plus, strong acid. All right, so we don't know which direction it's going to move, so it's good to calculate the value of Q so we can compare it to the value of Ka, and so that tells us which direction the reaction will move initially. When we calculate the value of Q, we get that Q is actually 0.00498, which is much greater than Ka. So the reaction is going to go in the reverse direction first. All right, I don't know what happened here. This definitely moved. I don't know why it did this. Well, I'll come back to that. You know what? I'm just going to eliminate that for the time being. So the first thing that we're going to do is we're going to run the reaction in such a way that we consume all of the acid. So we're going to run the reaction to consume all of the acid that we have there. We're going to put that to 0. We're going to add to the concentration of the acid, but because we're using the H plus, we are also going to consume some of the conjugate base of the weak acid. So the new, quotes, initial concentrations are going to be as follow. And now we can do the problem like we normally do for a typical equilibrium problem. With these new concentrations, I don't even need to do that. I just go directly to Henderson-Hasselbalch. I put my value of pKa down here. Then I take my concentration, the new concentration of the conjugate base, and I put it on the top part. I take the new concentration of the weak acid, and I just calculate what the pH is. And when I calculate that, it gives me that it's 4.75. 4.75. And the pH was 4.76. We added 1 milliliter of 1 molar hydrochloric acid. If we had added that to an equivalent amount of water, the pH would have gone from 7 to approximately 1.5. All right? So it is a very, very, very significant value. If we, instead of adding 1 milliliter, added 10 milliliters of the hydrochloric acid, the pH change would still not have been very significant. It would have only gone down to 4.76. At that point, the pH would have gone probably to, with 10 milliliters, it would have gone to approximately 1 as opposed to 1.5, or it would have gone about to 1. So very, very big changes are avoided in the presence of buffers. If instead of adding strong acid, I added strong base, all right, well, what is going to happen is instead of reacting with the conjugate base, it's going to react with the weak acid, all right, and we're going to make more of the conjugate base. Just like before, we want to find out what the concentrations are going to be, all right. We want to find out what's going to happen, how much is going to be neutralized, all right. So the first thing that I like to do, and we can do it with stoichiometry, we can do it also with concentration, but it's not a bad idea to do it with stoichiometry, all right, is find out the number of moles of everything that you have there. So find, not in concentration, notice that we're looking at the overall equation. We're not doing equilibrium analysis. We have the base and the acid, which are going to be reacting, and we have how much of the salt we had. We're going to calculate the number of moles, not concentration, the number of moles that we had. All right, and so we use our normal equations. Remember, number of moles is equal to concentration times volume, and the volume has to be in decimeters cubed. And so that's how we find out that we had 0.01 moles of sodium hydroxide, 0.05 moles of ethanoic acid, and 0.05 moles of sodium ethanoate to begin with. The reaction takes place. We're going to consume all of the limiting reagent, in this case the sodium hydroxide, and that's going to consume some of the acid, but it's going to produce, we don't worry about producing water because that's not relevant to our calculation, but we're going to produce some more sodium ethanoate. All right, and so we now have two new number of moles of these two species, the acid and the conjugate base. If we divide by concentration, sorry, if we find the concentration by dividing by the total volume is now 210 centimeters cubed, or milliliters, or 0.21 decimeters cubed. Why? We had 0.2 before and we added 10 milliliters, so it's going to be 210 milliliters. All right, we now divide 0.04 by 0.21 and we get that this is the concentration of the acid. We divide 0.06 by 0.21 and we get that this is the concentration of the conjugate base. We can put that into the equilibrium analysis. We don't have to go very far. We just go directly into the Henderson-Hasselbalch. All right, pKa plus the concentration of the conjugate base over the concentration of the acid. Again, when we do that and we calculate, we find that the pH has increased to 4.94. Again, not a significant pH increase. Remember, this time we added 10 milliliters, not just 1. So it's not a very large increase. If we had added that to pure water, the pH of the pure water would have gone to 13. All right, so it is definitely a very small amount. All right, and especially when we consider that we actually neutralize 1/5, all right, or 20% of the buffer. All right, that is not a significant change. All right, if we instead had only added 1 milliliter of the sodium hydroxide, the pH would have remained still at 4.76. So that is how good a control of the pH a buffer has. All right. If we have basic buffers, let me try that again. Basic buffers are made with a weak base and the salt of its conjugate acid. All right. Now we're going to. It's exactly the same process, except that the Henderson-Hasselbalch equation takes the form of the POH. So POH is equal to pKb plus the logarithm of the conjugate acid over the base. So notice that always in the Henderson-Hasselbalch equations, the conjugate goes on the top and the original acid or base goes on the bottom. All right, and then because we want to find out pH, once we have POH, we do 14 minus POH to find out the pH. So that is the key formula that you need to know in order to do basic buffers. All right, and again, for those of you who are in my class who actually have the handouts, I don't want to spend too much time going through this. I just want to show you an example of how we can calculate the pH of a buffer. All right, but the equations are going to be very much the same. So if we have a buffer that was made by dissolving, I'm going to make it slightly different this way. Dissolving 1 gram of ammonium chloride in 100 milliliters of 0.2 molar ammonia. All right, we're going to assume no change in volume. All right, so we already have the concentration of the ammonia. We all need to do is see, okay, well, how many moles is 1 gram of ammonium chloride? All right, in this particular case, I divide 1 gram, and I get that 1 gram is 0.0198 moles of ammonium chloride. All right, we divide that by the total volume, which is 0.1, and we're going to get that it is 0.98 molar, the concentration of the ammonium chloride. All right, so we're just going to go ahead and put that directly into our Henderson-Hasselbalch equation. Here are the things. We take the value for the conjugate, and that's always going to go on the top of the logarithm. And we take the value for the original base, and we're going to put it at the bottom. We are going to look in our data booklet for the value of pKb for ammonia. And when we look at the value of pKb for ammonia, we find that it's 4.75. All right, and that's why that value is there. And now we just calculate, and we find, because those two concentrations were very similar to one another, all right, we find that the pH in this the POH in this particular case is 4.75. It didn't change, all right, because this is almost 0. All right, and so the value got lost in the significant figures. And then pH is going to be 14 minus 4.75, which is 9.25. All right. If we add a strong base, all right, how would that change it? Well, if we add a strong base, let me just go back to the equations here. If we add a strong base, we're going to increase this, and that is going to then consume and react with some of the conjugate acid. So it's going to decrease the concentration of the conjugate acid, increase the concentration of the base, and those are the values that you're going to again put one more time in there. All right? So let's look at an example of that. How would that happen? If I add 1 milliliter of 1 molar sodium hydroxide to the buffer that we had just made, all right, first of all, we need to calculate the new concentration. We have a new volume. It's not 100 milliliters, but it's 101 milliliters. All right, and so we need to make sure that we calculate all the new concentrations for the ammonium chloride, for the ammonia, and even for the hydroxide ion. All right, sodium hydroxide. So these are the ones that we're going to calculate using our usual equation for dilution. M1V1 is equal to M2V2. M just being the value of the molarity. You could use C if you're used to using C for concentration. All right. So we got those values, and here they are. Now, all I'm going to do is, okay, I have the new concentrations. All right. I can completely, I can use this directly if I want to, all right, because if this goes back, it's going to consume some of that. You're like, oh, how do I do it? So what you're going to do is figure out which way is the reaction going to be moving, all right? So you need to calculate a value of Q. You're going to put Q, and you're going to compare the value of Q to the value of K, KB for this reaction, which you have calculated from the pKb that you can get from the data booklet. All right. Now, because Q in this particular case is much larger than KB, the reaction is going to react in the reverse side. So we're going to, again, this is here confusing things. We're going to consume all of the hydroxide. All right, and we're going to consume some of the ammonium ion. I'm going to produce some more of the ammonia. So we're going to have a new concentration. All right, we could do this with moles, but because in this particular case the overall concentration is not changing, we're just going to leave it like that. And so we have these two new values. We don't have to do any more analysis. We could do this analysis, but there is no point in doing that. We can just take the new values and inject them directly into the HendersonHasselbalch. When we do that, we see that the value of the pOH changes to 4.70 from 4.75 before, and the value of the pH increases to 9.3 from 9.25 before, but the increase is not very large. It's almost no change in the pH, which is again acting as a good buffer. If we add a strong acid to a basic buffer, we first have to do the neutralization. So we have to do the stoichiometric analysis. We have to go back to moles. And so we've set the entire equation. We have ammonia plus hydrochloric acid going to make ammonium chloride. So we calculate the number of moles. I'm not going to go through the process of calculating each one of the number of moles, but we have that is 0.02 moles of ammonia plus 0.01 moles of hydrochloric acid. And we had, remember from our calculations, 0.0198 moles of ammonium chloride. This is from the very beginning of the buffer. So if we consume all of the hydrochloric acid that was added, that's going to be our limiting reagent. We're going to subtract from the ammonia and we're going to subtract from the hydrochloric acid, but we're going to add to the ammonium chloride. We have now new concentrations of the ammonia, new number of moles of the ammonia and ammonium chloride. We divide by the new total volume, which is 10 milliliters plus the 100 milliliters that we had before. It's 110 milliliters, and we get our two new concentrations, the concentration of the ammonium chloride and the concentration of the ammonia. We can put this directly into the Henderson-Hasselbalch. Again, one more time, I'm just in a circle, which goes where? And we can calculate directly the value of pOH, which in this case is going to be 5.22. We have definitely have a change in the pH, but the change in pH is not as significant as it would have been were this not a buffer. All right, and then 14 minus 5.22 is going to give us 8.78, which is the final pH for our reacted buffer. All right, so it is a large pH change, all right, compared to what we had before. But remember, the original pH would have been 9.25. But if you have neutralized 50% of the buffer, that is quite significant. If you had neutralized 50% of just the ammonia present there, all right, the pH would have changed very, very dramatically. Not just half a pH unit, all right, but it would have changed much, much more than that. All right, so here are a couple of tips when you're looking at buffers and making buffers. If you are asked to make a buffer, you want to have a buffer that has a pH near the pKa for the pH that you want. So you want the substances with which you're making, the acid with which you're making the buffer, to have a pKa similar to that of the pH that you're asked, you need to have that buffer. All right, or if you're doing for a base, you want the pKb close to the pOH for that substance. All right, for the buffer that you want. So if I want a buffer that has a pH of 3, all right, I would look into my acids and see which one has a pK value of pKa that is close to 3. So if I keep on looking, I would find that bromoethanoic acid has a value of 2.90, or even iodoethanoic acid has 3.18. Those two would be good choices because they are close to the value that I want for my pH of the buffer. And then I would use the conjugate salt for one of those. All right. Preferentially, I would use bromoethanoic because it's closer. All right. Second thing, for the buffer to be act best as possible, you're going to have the buffer have a 1-to-1 ratio of acid and conjugate base. All right. That way, the pH is very much the pKa, and second, it can equally well balance or neutralize addition of acid or addition of base. All right, and finally, you want the highest concentration you can have for your acid and conjugate base, because that will give it a much greater buffering capacity. The larger the concentration is, the less the concentrations are affected by addition of small amounts of acid or small amounts of base. All right, and that is it for buffers. All right, there's just one more video for acid and base, and we will be done with this chapter. Thank you.